Hello everyone, and welcome to this new technical series on reliability engineering and risk assessment. For over 40 years, ITEM Software has been an acknowledged world leader in the supply of reliability, availability, maintainability, and safety, or RAMS, evaluation tools. Whether you are working in aerospace, energy, or manufacturing, understanding and mitigating risk is critical to operational success. In this series, we are going to break down the core concepts of risk analysis and show you how ITEM's suite of products can help you perform these complex evaluations with precision. In this technical series, we will explore the core concepts of risk analysis and the common methodologies used to perform it. We will walk through the step-by-step process of modeling a system using a real-world example and show you how to interpret those results to make informed safety decisions. In part 1 of the series, we are starting at the very beginning with the fundamental concepts of risk analysis. Before we look at models or software tools, we first need to understand what risk means in an engineering context. The primary objective of performing a risk analysis is to move from reactive troubleshooting to proactive system management. We start by looking at our systems and processes to determine the potential undesirable consequences that could occur. It isn't enough to just know what might happen. We have to identify the specific pathways, the sequences of events, that allow those consequences to actually materialize. Once we have mapped out these scenarios, we use analytical techniques to estimate the likelihood or the mathematical probability of these events occurring. This data-driven approach allows us to provide decision makers with the concrete technical input they need to select the most effective and optimal strategies to reduce risk across the organization. To analyze risk effectively, we must first establish a precise definition of what it is. In a professional RAMS context, risk is characterized by the presence of two essential elements: uncertainty and undesirability. For a situation to truly be considered a risk, both elements must coexist. If an outcome is certain to happen, it is a known issue rather than a risk, and if an outcome is desirable, it represents an opportunity. We evaluate these two aspects as the likelihood of an event occurring and the severity of its impact. Once we have defined risk, we need a way to measure it so we can make objective decisions. We evaluate risk using two primary metrics that you will often see described with different terminologies. Some professionals refer to these as frequency and magnitude, while others use likelihood and severity. Regardless of the terms used, they represent the same core concepts: how often an event is expected to occur and the total scale of the direct and indirect consequences if it does. By measuring these levels, we can compare our findings against established acceptance or tolerance criteria. This comparison is essential because it tells us whether the current risk level is manageable or if it requires further intervention to meet our safety standards. A professional risk assessment is built on providing data-driven answers to 4 essential questions. We begin with the most basic: what can go wrong? This involves identifying every potential hazard or failure mode within the system. Once a hazard is identified, we ask, what are the consequences? Here, we look at the potential impact on safety, the environment, and operations. The third question, how frequently might they happen, moves us into probability and frequency estimation. Finally, we must address our own uncertainty by asking, how confident are we about our answers? Whether the system is simple or requires complex modeling, these 4 pillars ensure a complete and robust analysis. Once the assessment is complete, we move into the vital stage of risk management. Our analysis provides the technical foundation for answering 3 critical questions. First, what can be done to prevent, mitigate, or detect these risks? Second, we must evaluate the cost associated with these safety measures. And finally, we look at the efficiency. How much safety do we actually gain for our investment? By providing these inputs, we help decision makers move beyond guesswork and select the most optimal strategies for reducing risk levels across the organization. To tie these concepts together, let us look at a risk scenario, which is the specific path from an initiating event to a final end state. This maps directly back to our fundamental questions. The initiating event is the what can go wrong, while the path shows exactly how that failure propagates through your system's barriers. The end state represents the final consequence, whether that is a safe shutdown or an undesired event. By mapping these scenarios, we can see exactly where a system is vulnerable and where our mitigation efforts will be most effective. To determine if a risk is tolerable, we plot our findings on a risk acceptance curve. This chart helps us visualize the relationship between the frequency of an event and the severity of its consequences. You will notice distinct regions on this slide. The unacceptable region at the top right, where risks are too frequent or too severe to be ignored, and the acceptable region at the bottom left. By mapping individual scenarios onto this detailed curve, we can identify which risks require immediate mitigation and which fall within our safety margins. This visual tool is essential for prioritizing engineering resources where they are needed most. While acceptance curves provide a more detailed quantitative view, risk matrices offer a simpler qualitative way to communicate risk. This simplified view categorizes different levels of risk using color-coded zones, typically green for acceptable, yellow for caution, and red for unacceptable. This allows us to quickly categorize various scenarios based on their combined likelihood and severity. It is a powerful communication tool that helps stakeholders immediately identify which parts of the system fall into high-risk zones and require priority action. In this first session, we have established the foundational language of risk by defining it through uncertainty and undesirability. We've identified the core metrics of frequency and magnitude and outlined the 4 fundamental questions every assessment must answer. Understanding these basics is the first step toward effective risk management. In our next video, we will build on this foundation by discussing the different methodologies used to perform risk analysis. We will compare traditional inductive and deductive methods and introduce how the item software interface helps you apply these techniques to your own systems. Thank you for watching, and we'll see you in part 2.